In this video, we're going to talk about another tool we use when solving probability problems, and that's called a tree diagram. Tree diagrams are used to help us determine the sample space for an experiment. They help me figure out all of the possible outcomes, and they also help us calculate probabilities using the multiplication rule. Meaning we often use tree diagrams when we're doing multiple events in succession, which is exactly what the multiplication rule is for. Each trial of the experiment, or each new thing that we do, results in another branching of our tree. We're going to do an example where we build a tree diagram and then use it to calculate some probabilities. So it says in a standard deck of cards, there are 52 cards. 12 cards are face cards, and 40 cards are not face cards. Draw 2 cards one at a time without replacement. Construct a tree diagram for this scenario, including the probabilities at each stage. So I'm drawing 2 cards. I'm going to have 2 sections of branches. I'm going to have a section for my first draw, and then I'm going to have a section for my second draw. So for that first draw, we're going to start at the top. I'm going to go out, oops, make that a little bit straighter. I'm going to go out, and I'm going to go out. And there are 2 possible outcomes here. When I draw a card from the deck, that card could be a face card. That card could be not a face card. And I'm going to label each of those branches with the probability of that branch. On my first draw, there are 52 cards in the deck. 12 of them are face cards, so the probability of drawing a face card is 12 over 52, and the probability of drawing a not face card would be 40 out of 52. I'm then going to repeat. For my second draw, the same options occur, face and not face, but it will look different depending on what I drew first, so I have to consider both options. I'll start with that first draw being a face card. And again, those same 2 options, face and not face. And then I'm going to calculate the probabilities. And I need to remember that when I did this, I am drawing without replacement. These are dependent, so those fractions are going to change. In both cases, the fractions are going to have a denominator of 51, because I've removed a card from the deck. If my second draw is also a face card, I have to worry about the fact that on the first draw I removed a face card. Now there's only 11 left in the deck. If my first draw was a face card, my second draw, not a face card, there should still be 40 non-face cards left in the deck. We're then going to do the same thing, assuming that our first draw was not a face card. And the same 2 options, my second card could be face or not face. I see a similar issue with the denominator. After my first draw, I'm left with 51 cards. If my first draw was a non-face card, I should still have 12 face cards left in the deck for the second draw. On the other branch, if my first draw was a no-face card, I should only have 39 no-face cards left for my second draw. And that is a completed tree. You will often see people multiply those probabilities down to get those final probabilities. I'm not going to do that here because that's asked for some of these questions down below. We'll come back and look at that in just a second. And the first one says find PFN. PFN. So this is P face card and no face card. I know that I'm multiplying. This should be P face card times P no face given face card. And we have that in our table. The face card, no face card branch is here. So I just need to multiply those probabilities. So it's going to be 12 over 52 times 40 over 51. Oops. Try that again. There we go. So 480 out of 52 times 51 is 2,652. Which is about 18.1%. Now that we know how we're calculating each branch, we're going down the branches and multiplying the probabilities. So I'm going to go ahead and do that for all of these. We just calculated this branch here, so I know what that looks like. That's going to be 480 over 2652. For the rest, it's a similar idea. So 11 times 12. Whoops, no, that's 12 times 12. 11 times 12. So this branch would be 132 out of 2652. The next one is, if I look at this guy, that's a 40 times a 12, which I just did, 12 times 40. That's also going to be 480 out of 2652. And then my last branch is going to be 40 and 39, which is 1560. Because this represents all of my possible outcomes, those probabilities should add to 1. So I'm going to check on my calculator. So 132 plus 480 plus 480 plus 1560 divided by 2652, and I do get a total of 1. So we know we probably did this correctly. All possible options, the probability should add to 1. So let's go ahead and answer the rest of these questions using our fully built table. The next one says Fn or Nf. So Fn or Nf. So that's these two probabilities, and I know or means add. So this is just 480 over, that is a messy line, over 2652 plus 480 over 2652. So that's going to be 960 out of 2652, which is 36.2% or 0.362. The next one says find the probability of no face given that the first one was a face. That is one of the individual probabilities on our branch. So find no face given face. Well, here's my face branch. Here is no face given face. So this is just 40 out of 51. or 78.43%. The next, we're going to have to look at our outcomes. So I'm going to write in a different color what each outcome was next to its probability. So that first branch was face-face. So this is our FF probability. The next branch was face, no face. The next one after that was no face, face. And then no face, no face. And that's going to help us with that next question, which says, find the probability that we have at most one face card. So at most means no face cards or one face card. So I know I'm adding, and I'm pretty sure that that should be 3 of the outcomes. We have no faces, one face, and one face. So we're going to go ahead and add those up. So our no face is 1560. And then I'm going to cheat a little bit because we already did the one face options. Those are up here. I know that the one face options together are 960. And that's going to give us 2520 out of 2652. Which gives us 9502. There is another way to get that. I'm being lazy. Notice I have 4 outcomes total. I know all 4 of those together add to 1. If I only want this chunk, I can do 1 minus the piece that I don't want. So another way to get this, I could do 1 minus 132 over 2652, words are hard. And if I do that on my calculator, I should get the same answer. And you'll notice it spits out that exact same decimal, 0.9502. And I can plug that into my calculator and see that I get a reduced decimal that's the same by pressing the math button and using that fraction menu. So both of these represent 210 over 221. This trick that we used up here is called the complement trick. And the complement trick is that I know that the probability of A should be equal to 1 minus the probability of not A. And not A is called the complement of A. Not complement as in saying something nice, but complement in math as in makes up the rest of the set. So A and not A together should be all of the outcomes. In our example, A was this chunk of the tree, not A was this chunk, and together they make all of the outcomes. A similar idea for our last example, it says P at least 1 face card. So this is 1 or 2. Whoops, I didn't mean to do that in red. And I'm going to do this with our complement trick. If I come up here and look for 1 face or 2 faces, that's all of this right here. The complement would be no faces. So I can do 1 minus the probability that I have no faces. And that's going to be 1 minus, and then I scroll up, and no faces is 1560 over 2652. So 2652 minus 1560, that's going to be 1092 over 2652, which will be 41.18%, 0.4118. We'd get the same answer doing the addition, but sometimes that complement trick is a little bit faster. And generally, statisticians are lazy. We will do things the fastest way possible because all things in the universe are lazy. If you've taken physics, you've heard of inertia, yeah? So both of these methods are correct. Pick one that makes sense to you. You'll see me use this when I'm trying to find the probability for everything but one option. And then the complement trick is typically faster. All right, if you have any questions on how to make or read tree diagrams, feel free to send me an email or drop by Thursday's office hours. Otherwise, I'll see you in our next video.